that I didn't apply.
I hit record.
Yeah, it happened early on in the year, like in November, December, that I didn't apply to a lot of other jobs. I did do some interviews, they didn't work out. So this one worked out, and I'm very happy that it did. And we'll see what happens in the future. Are there any questions about kind of my situation, anything that I should discuss?
Are there any questions I like to pose?
Yeah.
I have one question about your job searching process. Like, I'm not sure how many files, like, how do you actually prepare your research proposal or like teaching proposal, those things during the job searching process?
Yeah. So usually if you want to apply for a research professor position, you want to have this research proposal prepared early on. So maybe before you start applying, you work on the research proposal and you have a lot of people check up on it. In my case, I hadn't planned on applying, so it was a last minute thing, but I had some ideas. Some of the work was an extension to my PhD work, and some other work was a new idea that I put, and it ended up working out. Um, there are a lot of resources that can help you out. So last year I attended at Berkeley around October, I think October or November, Rising Stars in Mechanical Engineering workshop, and it's a 2-day workshop, and it's held every every year, either at Berkeley or MIT or Stanford, and they give you kind of talks and advice about applying for these positions, research professorships, and in general positions in academia. So I would encourage you to apply and benefit. Ask your professor to recommend you to these talks and workshops. Anything else about, yeah? Okay.
Academia search or kind of, idea or grad school about Berkeley?
Oh, one other thing I recommend is, for example, I think that Berkeley is they're recruiting professors this year also in fluids and dynamics. So if you have the option to volunteer to be on the student committee that interviews the candidates, that will give you a great chance to learn about the interview process and what the universities are looking for.
Are there any other kind of questions about, academia job search? Questions about,
If there aren't any, then maybe we'll just start with the talk and we can take any questions at the end.
That's it. Thank you.
Okay, well, okay. So throughout my PhD, it was eventful. There was COVID and there was also the GSI strike, but it was divided as follows. The first 2 years I took classes and I did my master's work, which was theoretical work on the treatment of constraints, holonomic and non-holonomic constraints in rigid bodies. Holonomic constraints are constraints that can be written in terms of position coordinates, and non-holonomic constraints cannot. So, and the next 3 years were more numerical work on kind of how to simulate systems of rigid bodies with constraints. And I hadn't envisioned how it was going to end up when we started. But let us see what happened. So we're gonna, in this presentation, we will, maybe I should mute this video.
Stop 3. Stop 4. Stop 5.
Okay, so in this presentation, we will look at the effect of constraints on 3 systems. The first one that you saw, a sphere rolling in the plane. And then this method of transporting cylindrical gas tanks, and then a planar version of this forced motion of a stack of blocks. They're supposed to be shaking. Okay. So our first endeavor is to explore the holonomy of a rolling sphere, but holonomy, what is it? The holonomy of a rolling sphere can be defined as the change in orientation of the sphere after it completes a rectangular path. So you can look at this figure. This sphere starts with this orientation, and after it has come back to its original location, its orientation has changed. So this phenomena where some of the properties of the rigid body return to their original locations where other don't is an illustration of holonomy, which is a consequence of the non-integrability of the constraints acting on the system. Another interesting application of holonomy is parallel parking. So you take the car from this configuration to the same configuration, but in a different location. And in this example, the sphere is tracing a rectangle. And we previously mentioned that holonomy can be observed by the change in orientation of the sphere as it traces the rectangle. But other ways to observe holonomy is to look at the co-rotational basis of the sphere at the beginning of the motion, at the end of it, it has changed. Also, if we follow a point on the sphere, its location is going to change from the beginning till the end of the motion. The rectangle we're tracing is as follows. It has a starting point S and then dimensions H2 and the width W, and H1 is a parameter that locates the starting point. And we can kind of find three angles by dividing these dimensions by the radius. Now, this rectangular path is composed of 5 rotations that we can compose to find a total rotation R about an axis S with an angle C. There are cases where holonomy vanishes, meaning that the sphere is going to trace the rectangle and come back to its original location. This happens when one of the two sides is a multiple of 2 pi, or if both of them are multiples of pi. We also notice that the axis of rotation depends on the starting point, but the angle of rotation does not. So in this example I'm going to play now, these two rectangles are identical, but the spheres, they start at different points on the rectangle, and we're going to see that they're going to come back to different orientations. So the starting point matters. Okay. Now, in addition to representing the total rotation using rotation tensors, we can represent the rotation using quaternions by applying Rodriguez's formula repeatedly. And what's interesting is that while Q is a representation of the angle of rotation times the axis of rotation, or sine the angle of rotation over 2 times the axis of rotation. And it's very interesting to note that we're rotating about the A1 and A2 axes in the plane, and we will get a rotation about, or a rotation component about A3, which is an axis that is perpendicular to the plane, outside the plane. Now, from this formulation, or from this representation of the total rotation, we can extract 2 special rectangles. What's special about them is that they have one of their sides a multiple of pi, which makes the rotation angle kind of proportional to the other side. And these special rectangles we're going to use later on to formulate the Euler angle representation of rotations using rectangles in the plane. Now, so far what we've done is that given a rectangle, we've traced it and we've figured out what is the rotation of the sphere undergone after tracing this rectangle. The question we now want to ask, if we want the sphere to be rotated by a certain amount, how can we make a rectangle, or what are the dimensions of the rectangle that when traced makes the sphere rotate by a certain amount? And we were able numerically to write an algorithm that given a rotation, for example, here the rotation by an angle 3 pi by 2 about this axis, it gives us the dimensions of rectangles that once traced yield desired rotation. And notice that the rectangles are not unique. So you can trace several rectangles and obtain the same rotation. A numerical swipe over all possible orientations shows us that we can probably obtain any rotation of the sphere by tracing one rectangle, except that this process involves numerical calculations. It's not straightforward. We cannot do it by hand. So then we ask ourselves, can we obtain a simpler result, maybe using Euler angles? And the answer is yes. I'm not going to go into the detailed calculations, but using the special rectangles that I pointed out in the previous slides, we can devise 3 rectangles that, when traced consecutively, rotate us each by an Euler angle about another angle axis consecutively. So in our paper, we provide the dimensions and orientations of these 3 rectangles, which you can trace sequentially to obtain the desired orientation. So you don't need any numerical calculations for that. That's an example of rotating the sphere by 3 to 3 Euler angles about the angles mu1, mu2, mu3. So this is the dimension orientation of the first rectangle, and whether you should traverse it clockwise or counterclockwise, the second rectangle and the third rectangle. So that's a very nice interpretation of the Euler angles. Okay, so in conclusion, any holonomy can be achieved using a single rectangular path. The Euler angles can be visualized with the help of 3 rectangular paths. And this work has application to motion planning of spherical robots, such as BB-8 and Omni wheels. Okay. The second topic we're going to discuss is on the dynamics of transporting rolling cylinders. And this topic was incentivized by this video that we saw on YouTube of this person carrying gas cylinders. I'm going to mute it and run it again. So this man is transporting the tanks by rolling them at opposite angles with the vertical. By propelling one of the tanks while maintaining point contact between them, both tanks can be transported together with their centers of mass moving in straight lines. We want to simulate this motion, and we want to look at the constraints that are applied to this system. So putting safety concerns aside, we are asking questions: is there rolling or sliding at the point of contact between the 2 cylinders? What are the range of feasible angles of inclination? And is it necessary to support the entire weight of both cylinders when transporting them? Now, I started by assuming that there's rolling contact at these 3 interfaces. So these equations say that there's just rolling contact at these interfaces. Now the points P3 and P4 depend on all the coordinates of the 2 cylinders. That's the contact point between the 2 cylinders. So formulating that rolling constraint is a little bit mathematically kind of tedious. But still we did it, and we applied Frobenius's integrability criteria to figure out if the system of constraints is integrable. And it turns out it's not integrable. And furthermore, it turns out that only 8 of these 9 constraints are linearly independent, meaning that if we want to simulate this motion, we will not get a unique solution. It's very difficult to simulate the motion of a system when the constraints are linearly dependent, because usually simulating the motion of a system involves inverting a matrix that contains the gradients of the constraints. So when the constraints are linearly dependent, the matrix becomes not invertible. So then we thought that actually, practically speaking, the normal force between the two cylinders is going to be probably very small. So we thought that the contact between the two cylinders is probably going to be a sliding contact. So then we reformulated our set of constraints to just include a sliding contact between the two cylinders, rolling contacts between each cylinder and the ground, and then supporting the upper cylinders at a constant height, constant angles phi1 and phi2. So meaning that they're just in the vertical plane. They're not inclined up, back or forth. And then we drive the first cylinder with a constant angular velocity about its axis. And we are actually able to simulate this motion. I'm going to talk more about the method we use to simulate this motion in the next part of the presentation. Now, our simulations show that the normal forces between the two cylinders are almost zero, which agrees with our assumption. So as the normal forces between the two cylinders are negligible, the motion of the pair can be modeled as the motion of two independent cylinders. So then we analyze the dynamics of a cylinder, a single cylinder, rolling in a straight line at a constant speed, and we ask the question, what is the optimum method of transporting one cylinder? Okay, so we will look at this one cylinder supported by a force Fa that has both horizontal and vertical components, and the center of mass of the cylinder moves at a constant speed in a straight line. Because of the friction force here, well, we want this contact to be rolling, so the friction force is going to be static. So owing to the limited amount of static friction, not all configurations of the inclined cylinder are possible for a given applied force. So only these configurations, for each angle of inclination theta, only a certain number of configurations is given in this region P. The configurations in the region U are not allowed. And if we increase the ratio R over H, the radius over the height of the cylinder, our envelope for possible configurations change. And if we increase our static friction coefficient, the envelope is gonna become bigger. Now, we can visualize the set of admissible configurations instead of in the theta and the normal force or the F3 force plane. We can visualize them in the F3 F plane. And here they're non-dimensionalized by the weight. And we can plot the static friction criteria in this plane as these red lines. So then the forces, so then in this plane, the force Fa has components F3 and F that we can write as linear functions of each other in this way. And if we want to minimize the applied force Fa, we want to minimize the magnitude of this force. In this graph, this is equivalent to minimizing the distance between the origin and these lines. And this happens in two cases, or actually three cases. The minimum point can be inside the boundary. For example, in the case of this line, the minimum, the point on the line that is closest to the origin is within the boundary of the static friction criterion. And the distance from the origin to the point on the line is perpendicular to the line. The other case is that the perpendicular distance, the shortest distance between this line and the origin, the minimum applied force Fa, is outside the boundary of the static friction criterion, so we have to go back to the boundary. This is the minimum Fa that satisfies the static friction criterion. So we can plot our results here. The red dots and the blue dots in the F3 over mg, F over mg space represent the minimum components of the applied force Fa. And we can plot the minimum applied force Fa. And you can notice that the minimum applied force Fa does not only have a vertical component F3, it also has a horizontal component. So friction actually helps you minimize the applied force. So then, applying the previous analysis to a pair of cylinders with a negligible contact force, we can determine the minimum forces needed to transport a pair of cylinders. The minimum force needed to transport a pair of cylinders is just the minimum force needed to transport one cylinder, applied to each cylinder. And we can also verify our results numerically. Since we're at it, we also talked about the holonomies of a rolling cylinder. So again, the holonomy of a rolling cylinder can be defined as the change in orientation of the cylinder after it has returned to its original configuration. The difference between the cylinder and the sphere is that the cylinder can either be inside or outside the region it's tracing. And this is going to change the holonomy of the cylinder, the change in angle. Now, mathematically, the difference between the two cases is that this vector E2 double prime from the Euler basis we used to describe the orientation of the cylinder, in case A points outside the shape that's being traced, whereas in case B points inside the shape that's being traced. And again, we can multiply the components of the rotations needed to trace these shapes to get the total rotation. So for the case of the rectangle, the total rotation is going to depend on the perimeter of the rectangle. That's also true for the case of the circle or any shape. The holonomy of the cylinder is going to depend on the perimeter of the shape you're tracing. Okay, so for a cylinder tracing a circle, the holonomy is going to be equal to C over R. And the sign is going to be different depending on which case we're talking about. But the change in angle is going to be C over R, where C is the circumference of the circle being traced, and R is the radius of the cylinder. This is kind of related to the problem. I mean, it's a popular brain teaser of if you have two coins, and if you want to rotate one coin about the other, how many rotations do you need to go back to your initial configuration? Also, this is a figure of the holonomy of the cylinder tracing a rectangle. And here the holonomy is C over R, where C is the length of the perimeter of the rectangle. Okay. Our last topic is about the dynamics of a collapsing set of blocks. Stacked objects are everywhere. For example, containers on a shipping vessel. There's a recent interest in robots stacking objects to build walls, or just stacking randomly shaped objects, and then people carrying objects. Now, modeling stacked objects is very complex because there are multiple friction interfaces present between each block, and there's a potential for impact and collisions, meaning that the equations of motion become discontinuous because there's impact. And two consecutive blocks can have different possible relative configurations with respect to each other. So when we define the contact between the blocks, we have to take into account all these possible contact configurations. Now, to study the dynamics of a stack of blocks, recourse to numerical methods is necessary. Earlier works for a single block model, the impact of the block with the ground plane using a single coefficient of restitution and integrate the equations of motion between impacts. So what I'm saying is that there are earlier works that have tried to model the dynamics of one block on an oscillating base. And there's basically been two ways to do it. Either they look at impact and they model impact using a restitution coefficient to relate pre-impact and post-impact velocities. And then between impacts, the equations of motion are smooth, so we can solve them. The issue with this method is that it doesn't deal well with accumulation points. Accumulation points is when we have many impacts in a short period of time. For example, if you have a bouncing ball, if you throw a bouncing ball on the ground, after some time, there's going to be accumulation points, so many impacts in a very short time interval. If we're trying to resolve every impact, then it's just going to be impossible. There's going to be too many impacts. The other set of methods to analyze a block and an oscillating foundation is to, instead of having impacts, you assume that the block rests on an elastic foundation. And then the equations of motion are continuous, smooth, and integrable. Now, these earlier works on the dynamics of a single rigid block resting on an oscillating horizontal surface show a range of complex dynamics, including sensitive dependence on initial conditions, bifurcations of periodic motions, and chaotic motions. As a result, one can anticipate a larger variety of complex dynamics for a system of stacked blocks. Now, before I go into the stacked blocks, I want to talk about the numerical method that we're using to solve the equations of motion. The numerical method that we're going to use was published in a paper in 2021 by Capobianco et al. People in Germany that have been working on these methods for a long time. It's called a non-smooth generalized alpha method for mechanical systems with frictional contact. This method is able to, as the name says, resolve non-smooth equations accurately without penetration of the bodies and resolve friction, which is discontinuous. And even here, you can see in the figure that it also deals well with accumulation points. So this is the bouncing ball, and the accumulation points are resolved at the end. There is no penetration between the ball and the ground. Also, this numerical method stabilizes the constraints at position, velocity, and acceleration levels. So not only do we have to satisfy that this distance, the gap distance between the sphere and the ground, needs to be positive. The sphere is not contacting the ground, but also G dot N satisfies the restitution coefficient. So the velocities satisfy the the velocities satisfy the restitution coefficients, so pre and post impact velocities at impact are related. And also G double dot N is 0. The acceleration of the sphere is 0 when it's touching the surface. So then to be able to simulate the motion of, for example, the sphere or then of the blocks, we need to formulate the gap distance constraints between the contacting surfaces. We also have to figure out the slip speeds between the contacting surfaces to be able to prescribe friction, to determine if friction is static or kinetic and prescribe it. Okay, so this is our setup, a sample configuration of planar vertically stacked blocks. A typical block I of width Wi and height Hi is preceded by block I-1 and followed by block I+1. And in our current analysis, the blocks do not need to be uniform. I think I'm running out of time, so I'm going to try to hurry up a little bit. So there are different possible configurations of the stack of blocks. You can see 5 of them here. So we need to formulate the gap distance for each case. And it ends up happening that we end up figuring out that it's much easier to formulate 2 gap distances for each contact instead of 1, which is kind of different than what we had for the sphere here. Okay, so then we applied our work to 3 systems of stacked blocks. The leaning tire of Liar is the first one. The leaning tire of Liar problem asks what is the maximum overhang of a stack of blocks like this. And we are able to replicate kind of this configuration in our code, get the correct normal forces that are acting on the stack. And if we displace the bottom stack just by a teeny tiny bit, 1% rightwards, the stack is gonna fall. I'm gonna show you the simulations in a bit. But for now, I'm gonna show time-lapse figures. After the leaning tire of Liar, which we kind of used to verify our simulation, we considered the column of blocks and an oscillating base. But we had a problem. The iterations would not converge. And this happens because when the code is solving for the motion of the stack, not only is it solving for the motion, but it's solving for the configuration of the stack. And the configuration depends on the motion, and the motion depends on the configuration. So what would happen is that the code would settle on a configuration and calculate the motion. The configuration would then change. And the motion would change again, and it would go back and forth like this. That's why convergence wasn't happening. So we introduced a small algorithm that kind of circumnavigates this problem. What it does is that it gathers the unique configurations that the code is going through. We fix the contact configuration, and then we solve for the motion, and we see if the motion is feasible for this fixed contact configuration. What we end up getting is that there are many possible solutions. So for example, that's one stack of blocks whose base is oscillating, and after 3 periods, we have several solutions, 13 in this case. We can see how one solution divides into many solutions. Now, this is due to the sensitivity of this system to initial conditions and to numerical errors. Okay, now if we plot well, first we define 1 over time to fail. The time to fail is the first time at which any 2 blocks lose contact. If we plot that as a function of the angular frequency of the oscillation of the bottom block, we will see that at lower frequencies, the block is less stable. At higher frequencies, the block is more stable, which conforms with the observations from one block. The next experiments we do are about sliding the bottom block. And we expect that if the velocity of the bottom block is small enough when we slide it, the stack, I'm gonna go to the figures. If the velocity of the bottom block is very small, all the stack is gonna move with the bottom block. If we increase the velocity a little bit, the stack is gonna slide and rotate on the edge of the bottom block. And if we move the stack fast enough, nothing's gonna happen. Like the magic tricks of if you had a piece of cloth, a tablecloth, and you were to slide it very quick, everything's gonna return back to its initial configuration. So we did these simulations, and we actually got that they conform with our intuition. We also played with the restitution coefficient. For all the previous simulations, the restitution coefficient was 0. But if we increase the restitution coefficient a little bit, a stack that would have previously been stable will collapse. And it will collapse more quickly if it was collapsing initially. Let me show you these simulations here. So that's the linearing of tower of Liar that is gonna fall if we move the bottom block a little bit. So that's not a very stable system. Okay, and let me show you the multiple solutions. So these are all the same system, the same initial conditions with the same excitation. And lastly, I'm going to show you the experiments of sliding the bottom block. Maybe I'll rewind a little bit. So that's sliding the bottom block quickly, but increasing the restitution coefficient. Okay. And in conclusions, our results agree with our intuition, and we can deduce something about just carrying a stack of blocks from these simulations, which is that once an instability has set in, we are not able to solve for the motion post that instability. So it's very hard. It's basically impossible to stabilize the stack once an instability has set in. Because if you want to stabilize it, you want to know what's going to happen to it. And based on that prediction, maybe control how you're holding a stack. But if you can't predict the future, then you cannot kind of prevent it. That's why a lot of the robots that carry usually carry one object at a time instead of many. Okay, that's it. Thank you all for coming. This was kind of a quick presentation highlighting kind of the big things that I did during my PhD. Let me know if you have any questions, and I'm always happy to chat with anyone about grad school or anything. My contact information is on my website.
One in the audience have any questions about anything?
I have a question. Did you by any chance notice that your analysis or numerical implementation was dependent on the number of blocks that you used when you were analyzing the color?
Yes. So we did some experiments with changing the number of blocks. For example, when we're oscillating the bottom block, when you increase more blocks, when you increase the number of blocks, it's going to become more unstable. It's going to fail quicker. And that's a figure that I'm actually working on right now.
Thank you.
You're welcome.
Yes. I wonder if the friction forces are considered between, the base and blocks and between those blocks.
I didn't hear that question very well.
I mean, have you considered the friction force between the blocks or between the block and the base?
All the contact interfaces have the same friction force.
So
yeah.
Adjustable. That means like maybe you can have larger frictional coefficient between the block and the base, and maybe smaller coefficient among blocks.
Yes, in the current code, the friction coefficients are adjustable for each contact interface. We didn't play with that though in these simulations. You can also change the dimensions of the blocks, but I didn't do that here.
I have another question about, because you said you can change the dimension arbitrarily. But in general, you consider the blocks as the rigid bodies, right?
Yes, these blocks are rigid bodies.
Because I feel like there are some analogy between like the blocks and maybe 3D printing, because you need to print things layer by layer. And sometimes the collapse can happen because the material is relatively soft. especially like using it in large scale printing technique. I wonder if is there any possibility that that can extend your research for softer materials like 3D printing gels?
Yes, actually, the code that we're using from the original paper, they do include flexible components, so it can be extended. Yeah, I do imagine that we can extend it, but we didn't really look into that. We looked at kind of rigid bodies and at this phenomena of an abundance of solutions from a system like that.
Hey Teresa, sorry, my
Hi.
but thank you so much for the talk. It was great. I'm wondering about especially the stacked blocks in the application of shipping containers, and if you think it would be easy to transfer your work to that case where instead of the base sliding like this, maybe it's going like this.
Yeah. So actually, for the blocks on a shipping container, what we once had a talk about it with my advisor, and what we thought is that it's what we would want to model is not the stack of containers on top of each other, but the stacks of blocks next to each other and how they would fall on each other like that. The containers on top of each other are secured, but maybe if, okay, and the containers are secured with the ground and they're at a distance with each other. So maybe we can kind of calculate the force that's acting on the edges of the containers, the bottom edges. And once if the force exceeds a certain value, their connection is gonna fail and then they're gonna fall. And we'll see how they fall. So yeah, that's something interesting I would wanna work on. Yes.
What type of solver do you use for your numerical?
So it's a non-spool generalized alpha. We do Newton iterations. So we have the equations of motion and the constraints, but not only do we want to satisfy these equations, we want to satisfy them and their derivatives. And these equations are going to change based on the configuration of the system. So they're case-wise equations that we're solving.
So at every time t during the simulation, you get the configuration and there's a unique, I guess, solution for, well, maybe not unique, but there's a solution, solve for the solution for at every time step.
Yeah, so every time step I solve for the motion, and then I solve for the configuration, and then I plug into the residual and I see if it's zero, and if not, I go back again.
Thank you.
You're welcome.
All right, yeah, you went three more. Yeah, all right.
Hello, I have a question regarding the holonomy of rolling spheres and cylinders. In general, when modeling real-life situations like this, how common do we get integrable or holonomic constraints? Or is that kind of more like a special case or less common?
No, so yeah, that's a great question. Anytime you're just restricting the position of a body, for example, I want this phone to move on the particular surface, you're restricting the position, then those constraints are going to be integrable. When you're restricting the velocity, then we're not sure if they're going to be integrable or not. For example, roll without slip, you're putting a restriction on the velocity. Now, the other issue is that you might have two individual constraints that are not integrable, but when you put both of them in a system, the system of the two constraints now becomes integrable. There are methods to determine that, the integrability of a system of constraints. This is called the Frobenius integrability criterion, but they're kind of mathematically tedious to apply. They involve a lot of derivatives and kind of you have a matrix that's composed of derivatives, and you want to find the null vectors of it and do a series of multiplications of matrices with the possible non-vectors. And you need to get all of the numbers to be 0 for all different configurations, so x, y coordinates and so on. So it's very restrictive having all the system to be integrable.
Thank you.
More often than not, what I found in my applications is that I'll do a numerical swipe and I'll find values for which the system is not integrable, and then I figure out that it's not integrable in general by finding exceptions. Yes.
Do you have any interest in exploring chaotic properties of systems as you add more blocks?
And it becomes periodic. Yeah, the issue with the blocks is that it's very chaotic. So we're not gonna find periods or resonance because it's very chaotic and very sensitive. One other thing that we can possibly explore with the stack of blocks is that, when we have a continuous column, we can explore its buckling properties. Maybe we can do similar things for a discontinuous column, or maybe the shearing of a discontinuous stack of small blocks. There is some similar research. So not too long ago, a paper was published about shearing of a stack of papers.
That's all the time we have for today. So once again, I'd like to thank Teresa for coming today. I really appreciate you coming from, all the way this evening. And yeah, so, Teresa's information is on our webpage. So if you have any questions, feel free to share any questions. And yeah, thank you so much for coming to Teresa today. It's very good to talk.
Thank you very much, Ian. You'll find my email there, and hopefully I'll be back in Berkeley this summer. So maybe I'll see some of you. Thank you very much. And thank you, Ian, for doing this. Have a good day.